Hello, this is Andrew Powell, and this is another YouTube video. This is going to be a little bit different from my other videos. This video is going to cover a presentation that I did, I think the week before last, for a Python meetup. The presentation, I think, was recorded, but there were some issues. I recalled the person that runs the Python meetup saying that there were some issues with the recording. So instead, I'm just going to do a YouTube video. I'm probably going to break this up into multiple pieces. In fact, during the presentation, I couldn't even do all the slides since I only had a 30-minute time slot. But I'm going to do a chunk of this presentation and then, create more chunks as separate videos. The full thing is pretty long, and since I don't have the pressure of time, I tend to ramble whenever I do presentations, and I really don't feel like doing video edits or cuts. So what we get is what it is. So without further ado, allow me to introduce cocotb, FPGA simulation with Python. If there's anything, if you only, for those who are actually watching, if you only learned one thing, the one thing to get from this presentation is um, you can do Python-based simulations for digital circuit designs using cocotb, and the big advantage there is you get to do your simulations while having all the access to the Python libraries and tools, which is incredibly helpful. So, all right, just to kind of like set up some context, there's obviously a whole bunch of challenges when it comes to doing digital circuit design for FPGAs. By the way, my background is doing working with FPGAs. I haven't really worked on any ASICs at all, but I would imagine all the topics discussed here are also applicable to doing simulations for ASIC designs. But personally, I don't have any personal experience working with designs that are targeted for ASICs. So with that out of the way, one of the major challenges is just taking some starting algorithm or a feature, and then targeting that algorithm so that it maps better to the underlying technology. An FPGA, a field programmable gate array, is an array of configurable logic blocks where each logic block could be configured to run as a combo logic and or sequential logic flip flops, and they're all routed together. So you're building a circuit, in other words. So something simple as an adder, or you have a bunch of math. You have to break apart, and then you section each piece off so that you can maximize your throughput. So that's one challenge on itself. Just doing a build. So unlike regular software where you compile the code and it runs in a processor and it executes like one instruction at a time, basically. When you run a design, when you build an FPGA design, so you start with a HDL, which is the languages that um, they're like the programming languages for digital circuit designs, hardware description languages. Those get synthesized into a net list. So a net list is composed of the primitives, which are usually LUTs and flip flops, and those need to get placed into the physical part and then routed together. So this process is pretty lengthy, even for simple designs, and especially when you're trying to maximize the resource utilization on your part. You're trying to fit as many features or fit as many features so you can maximize whatever requirement like throughput or minimize latency, or just try to get as many operations in as possible. When you get closer and closer to the boundaries of the chip, it becomes harder and harder to get through the whole build process. So that's pretty time consuming. And while you're doing all of that, you might have to worry about external interfaces. There might be a processor that you're trying to speak to, or there might be a DDR interface that you're trying to write to. There might be some MDTs, mega gigabit transceivers. There's a lot of considerations when building a FPGA design. And of course, once you're running on hardware, unlike a lot of microcontrollers or processors, you actually have very little visibility. I know this is highly dependent on the technology. If I'm not mistaken, I believe microchip devices, they have ways where you can actually look at the registers as it's running. But I believe for the most part, if it's a Intel device, Altera or Xilinx, it's actually kind of difficult to see what's happening while your design is running. if you don't already have registers or you don't already have a like integrated logic analyzer in your design, um, you basically have zero visibility on what's happening while it's running. So sure, you might have all the speed that comes with running on hardware, but you don't have any visibility, so it's really difficult to confirm that you're meeting requirements. So what's the solution? Solution is obviously to build a simulation, right? So with a simulation, your external interfaces could be modeled, so like the environment. So you can have a memory that implements that DDR interface, and it just runs in the simulator. Then you can even take the block or the HDL that's targeted for hardware, and then compare it against actual data to make sure that the HDL behaves exactly how your original feature or original algorithm is stated to behave. One important factor is ensuring that the different various states that your system is in um, is basically checked. So there might be a common case, or there might be some extreme cases that are unlikely, but you still need to make sure that if the system ever reaches those states, that it behaves in an expected manner. So that's functional coverage. That's super important. Something that you can't easily do while trying on hardware, but you can do in simulation. You can track throughput, latency, um, and of course, you have full visibility in your design. So basically, simulations are extremely helpful when it comes to ensuring that your designs work. And the catch, though, is that in order to have an effective simulation, they take time and effort to kind of build up. And that's a lot of times a big deciding factor on how much effort you spend on your simulation is, well, how much time do I have? And maybe I can get away with just running things on hardware. But if you have the simulations, it's always a good thing. So the traditional solution is just doing an HDL test bench. I don't know if I explained this HDL hardware description language. That's either usually VHDL, Verilog, or System Verilog. I know a lot of verification test benches these days are written in System Verilog because System Verilog is effectively its own like high level language of a lot of bells and whistles that comes with a high level object oriented type language. Test bench just refers to the design that it's not going to run on hardware, but it's built specifically for the purposes of just testing your device under test, the DUT. Um, and like test benches could range in different levels of like complexity. What's probably most common is your peek and poke directed type testing. I don't know how common the term peek and poke is, but I know where I work that's used a lot to refer to the most basic of tests. And those tests could just be stimulus into DUT. And you kick off your test and you just look at the waveforms to see whether or not anything comes out. And for a lot of engineers, that's like, all right, good enough. Let's just build the thing and then run it on some test hardware. And you can get away with a lot just by you can still learn a lot just by doing something as simple as that. And it doesn't take obviously it doesn't take any time really to build a simple peek and poke test bench. But on the other end of the spectrum, you might have a UVM. I think that stands for Universal Verification Method type test bench, which has a whole lot more bells and whistles. And the intent with these test benches are, you have monitors, drivers, actually interact with the various interfaces of your DUT sequencers, represent the streams of data that you use to drive into the drivers and into the DUT. Monitors are passive, so they just check the states of your DUT. And then a scoreboard is the scoreboard is more of an elaborate system in itself, where it takes those passive streams of information and then scores it. Right, scoring involves could involve actually comparing against a model, doing functional coverage. You could have any number of operations in the scoreboard. But obviously, there's a lot of benefit that you get from having a more sophisticated test bench. But like I mentioned, it could take a lot of time and effort to get something like this. So, what are some of the challenges with HDL test bench? Well, part of the reason why it could potentially take a long time to develop something more sophisticated is it's you don't really have a lot in terms of accessible libraries and like useful tools to kind of help you to build up the test bench. And I'm saying this relative to alternative solutions. There's no like package manager where you have like 500,000 plus libraries at your disposal that you can leverage from. Um, in fact, usually what you have is custom libraries. Oh, you might be very reliant on the vendors to provide you with tools. As far as I could tell, there's very little in terms of like community. And I say that, like I said before, relative to alternative solutions. There is, a FOSS community that does, work on useful tools. Like, in order to do this whole presentation, I used, GHDL and cocotb. Those two tools alone are, free and open source. So it's there. It's definitely there. Excuse me, I'm like drinking coffee while doing this presentation. Um, HDL, whether for synthesis or verification, can take a while to write in. So just the act of writing in most HDL languages, this is mostly opinionated, but in my experience, and I've been writing in, Verilog and VHDL, now mostly just VHDL for probably as long as I've been writing in Python. And in my opinion, writing in Python tends to be a lot quicker for what you can do. At least specifically when you're writing more software, code as opposed to HDL. Like HDL languages are really good at writing digital circuit type designs. Obviously, they're made for that reason. Heck, there are features in HDL languages which I wish other languages also had, or at least Python. But for the most part, it generally does take longer to write the same thing, in my opinion, in most HDL languages compared to alternative solutions. So here's the alternative solution, right? So this is a good time to mention cocotb. Cocotb stands for coroutine co-simulation test bench. Coroutine refers to the fact that cocotb incorporates a cooperative scheduling system to insert itself within the simulator's scheduler. I'm really going to drive home this idea, but the scheduling system of cocotb effectively makes cocotb a process within the realm of VHDL. One thing I probably should have mentioned earlier in this presentation is that I know I do write some stuff in Verilog. I used to write Verilog a lot more um, before working full time, but I mostly just write in VHDL. So all the examples are going to be in VHDL. So coroutines of co-simulation refers to the idea that cocotb, um, it doesn't like replace a HDL test bench. You technically still have it, right? Um, so like you swap back and forth between the cocotb scheduler and the VHDL scheduler during certain conditions. So if you have models or other designs that are test bench oriented but they're written HDL, cocotb doesn't prevent you from using any of that. In fact, the way it works is cocotb inserts itself into the simulator's event-based scheduler using a system called triggers, which are effectively the wait statement in VHDL. So if you already are familiar with the wait statement in VHDL, then you're pretty much already familiar with triggers. And then it's just a matter of understanding the keywords and maybe the syntax differences, but they effectively do the same thing. And of course, cocotb is intended for making test benches. The idea is that you want to test your design in Python. So, and the one cocotb component that I kind of attach to testbench is simulation handles. Simulation handles are just the references in Python that allow you to access the corresponding simulator objects. So more about that, as we continue on in the presentation. So what's the advantage of cocotb compared to traditional HDL test benches? Well, I already mentioned this, but like the advantage is really just boils down to you can write your tests in Python, um, which I know sounds pretty simple, but anybody who's familiar with Python already knows the advantages of writing things in Python could get you. And if you're able to write your simulations, or at least a portion of your simulations in Python, you gain advantages like access to a really big, free and open source community. There's a whole lot of different libraries. Like the PyPy repo alone has 500,000 plus Python distributions. Obviously, you can argue like how many of those are even pertinent to doing simulations. Well, having access to so many Python distributions, you'll be surprised to find how many become surprisingly useful when you don't have to write custom libraries to do things like signal processing. Um, there's even like PyUVM. So I actually have a PyUVM example. I'm not going to talk about it in this presentation. It's part of my example set that I did with this presentation. But you can do UVM in Python. There's cocotb coverage for functional coverage, and I believe cocotb coverage also does constraint random. The example that I have, I think, only covers the functional coverage. I need to at some point I'll do an example that does constraint random. Um, but those are all options. The cocotb-introduction repo that I'm going to mention later, it's going to contain tests that demonstrate those two pretty important Python distributions. And then of course you just have other stuff, right? NumPy gives you operations like matrix operations, FFT. There's a PyPy fixed point library. I haven't used this one personally, so I can't say from my experience how close it is to the VHDL fixed point libraries, but I would imagine it's pretty close, if not bit accurate. Hopefully, it is bit accurate. We need a JPEG. Well, there's PyLib JPEG. There's any number of like PyPy distributions that are very easily accessible using one of Python's packager tools like pip. In order to do the cocotb introduction repo, I actually use Poetry. I assume it's using pip under the hood, but I kind of like Poetry because it makes it easy to set up, a virtual environment. Um, Basically, long story short, you have access to a lot of reusable code, and that alone is a huge benefit that Python has that I think conventional HDL languages don't have. Like I said before, with HDL languages, you either have to write something custom or rely heavily on whatever libraries the vendors can provide. But with Python, well, you have access to so much more than just that. And because the nature of how cocotb works, it doesn't prevent you really from using other tools in HDL. Python is an extremely productive language. Again, some of this stuff is kind of just opinionated, but I find it when it comes to writing simulations, it's much faster to write a Python script compared to just doing everything in HDL. Python is relatively easy to learn. Um, for somebody who already has a lot of experience writing in a language like System Verilog, obviously it might be faster initially, but if you can write, I've written stuff in System Verilog. If you can write System Verilog is like C++ in my opinion. It has every like computer high level computer language feature under the sun. Um, if you can write in that, you can most certainly write in Python. And because it's easier to write in Python, I feel like Python is easier to maintain in my opinion, compared to a lot of HDL. I think part of it's because of the massive support that it has when it comes to libraries. You have tools like Flake8, Black, iSort, things to maintain the code quality. Of course, you have similar tools for HDL. I, I can only think of Sagasi from the top of my head, and I'm not even sure if Sagasi does. Making sure that the all the you know all your conventions are followed when writing VHDL. Um, but in my opinion, there's far more tools and far more easier tools to use when it comes to ensuring that the quality of your code is maintained and it's well documented. And when it comes to Python, um, a nice touch is Python because Python is an interpretive language. You don't need to recompile all of your HDL when running your tests. You could just start your test over and nothing needs to get recompiled. And again, there's a high focus on just getting the test done. That's really the big advantage here when writing in Python. Just getting the test completed and running, is the big advantage. Spend less time doing development that way, and then get closer to having something that works and does what it needs to do. Um, and Python can easily access other programming languages. I don't know how common this is said, but it is said that Python is a it's an excellent glue code, like a glue language, since because it has so many Python distributions, there's almost always a Python distribution that involves getting access to other languages. Like I know there's a distribution that allows you to get Java into Python. There is PyBind for C++ or C types, but maybe you really should be using PyBind whenever you can. Um, there's so many options, and of course you can even consider cocotb a tool that allows you to get access to HDL within your Python. So yeah, big too long didn't read. The big advantage of Python is that you're able to kind of get your stuff done quicker just because of how productive the language is. It has a lot to offer. So I think it is, worth it to kind of mention some of the limitations. In my opinion, a lot of these limitations, it's not really CocoTB's fault. It's the limitation of the simulator. Um, but I know it's going to feel like it's CocoTB's fault for people who are using for the first time. If you don't know any of the internals of how CocoTB interacts with the simulator. So if you're trying to do everything like completely free, and you're just using a FOSS simulator, like for all the examples here, I I used GHDL, and from my knowledge, there's no simulator that does multi-language support, and I know for a lot of businesses, if not most businesses, they need to be able to have a simulator that can do multiple languages like VHDL or Verilog together. So CocoDB can do it, but you're likely going you're going to need one of the commercial brand simulators. Like at my job, we use Questo, and the support for Questo is pretty damn good, honestly. Um, at least recently, and I haven't had any major issues using Questo, but that supports different languages. Um, I think there's still going to be a few hiccups here and there, but for the most part, it works pretty smoothly. But if you're using like either Icarus or GHDL, like in my experience, I've used Icarus, GHDL, and Questa. Those are, at least in terms of using CocoTV, those three simulators are the ones that I have extensive experience in. Um, Icarus obviously only does Verilog. Well, maybe not obviously, but Icarus is a Verilog simulator. Works really well, but it only does Verilog. And I have noticed that there are some limitations with what you can do depending on the simulator. And all those limitations, at least in my experience, have to do with the simulation handles. From my understanding, the reason why there is differences in how the simulation handles work, or what really the simulation handles can access, is due to the internal like APIs that the simulators have to implement that grant CocoTB access to the simulators objects. So, and this is something that needs to get tested. I know that in theory, the your Python tests using CocoTV are going to run slower compared to the same tests that are fully implemented in HDL. In fact, it is recommended that certain features or certain operations are just done in the HDL test bench side, like for instance, driving clocks, because swapping back and forth does incur a little bit of an overhead. When I say swap back and forth, I mean swapping back from the simulator to the Python interpreter. Unfortunately, I don't know. I don't have any numbers as to how bad it is. So that's one thing that might be good to kind of keep in mind. At some point, I'll add an issue to my cocotb-introduction repo just so I can do some tests and have some form of numbers. The one big thing is, like I mentioned, is the clocks, right? I'd be curious to see how much benefit you get from moving the clock out of Python and into the HDL. And then I think one disadvantage that's definitely worth mentioning, because I know some people are going to ask about it, is, well, can you use the Python debugger? The answer is yes, you can. But there is some bit of effort that you need to put into using the Python debugger. I'm not going to get into it here, mostly because it's been a while since I've used the Python debugger with cocotb. But it involves starting simulator first, since simulator is actually the one in control. You start everything up from the simulator, and the simulator um, under the hood starts up the Python interpreter, and then you got to attach it. So somehow, when your simulation starts, you need to make sure that it doesn't run, but then you have to attach the process to PDB as like in a separate window, and then you can continue. So it is a bit more effort to kind of get the PDB up and running, but it is doable. I guess before I get into the actual going over a cocotb test and how it interacts with the simulator, I do want to talk a little bit about the cocotb-introduction repo. So there's going to be a link here. I'm going to post a link to the slides in the repo. In fact, I'm just going to post a link to the repo in the what's it called? In the, I guess, the status bar of the YouTube video, so you can get this. It's going to have a link to the slides. It's already 26 minutes in. This is going to be the last section I'm going to cover before stopping this and then creating another video where I continue. But so yeah, I created a repo that has all the examples that I'll go over in this presentation, or I guess the second part of this presentation, and then it also has a bunch of other tests as well that I don't talk about in the presentation, but they're good to use as a reference to kind of get more information about how cocotb works or what you can do with cocotb. Um, so yeah, these are there's the functional coverage example, UV example. These are obviously more advanced, but they're just kind of there to show you can do it. So, and this is just a quick. This is all part of the README that kind of explains what you need to do to get things started. Yeah, you are going to need these dependencies. I used Windows Subsystem Linux, or Windows Subsystem for Linux. Um, Basically, I used that in order to do all the build up the whole stack and do all the examples for this test. I'm pretty sure. Actually, I'm not 100% sure. I think you can run this directly in Windows, but I think you need to use WSL to do it. Normally, you want to use Linux. I think years ago I tried running this directly in Windows, and I think I remember having a lot of trouble. I don't know. It's been a while since I've done it directly in Windows. It's much easier just to run everything on WSL. I use Python 3.11.7, um, so you don't need all of Anaconda, but I do suggest getting Anaconda since it'll have everything that you can possibly need. Poetry is important because that's how I set up the virtual environment. So once you have Poetry installed, then it's simple as cloning down the repo, Poetry shell, Poetry install, and then installs all the Python distributions that I used. And then you type in inv, shows you all the commands you can run, and these commands are all the tests that you can actually execute. Um, um, okay, yeah. So the commands you can execute from the tests folder when you enter the repo. And of course, they use GHDL. That was the simulator that I used. Um, so I mentioned, so I recommend building GHDL from the binary. When I tried installing GHDL from apt, it gave me a much older version of GHDL, which didn't have it didn't support all the libraries when I was running when I was building the VHDL 2008 HDL. So I did use a bunch of features from VHDL 2008 in order to write up the examples. So just keep that in mind. And then of course I use GTK Wave to kind of view the waveforms, the VCD files that are produced by GHDL. All right. Um, so I'm not going to get too much into this. In fact, I'm actually going to recommend that you don't follow the same flow that I did. So CocoGB supports a makefile system if you just want to get tests up and running. Um, so I just found this out recently, but apparently there's a much better way using PyTest and I think PyRunner to run tests. So this is actually an older approach where it uses a makefile system. This is part of the reason why I think I needed to use Linux, so I had access to Make. But I don't think you need to use the same approach anymore. It still works, and this is what I did to run the tests for this for the cocotb-introduction repo. But I do recommend looking into the cocotb documentation and finding the I think it's called the PyRun or the PyTest approach, which is most certainly more preferable than dealing with makefiles. Um, all right, so I'm gonna actually end the video right here. I didn't really cover any of the cocotb like examples. Really, it's just one big example, but it kind of goes over everything that you need to know. So, and this video is already gone up to 30 minutes. Um, I was able to get through this material a whole lot faster when I was doing the presentation. Like I said, I do tend to talk on and on. Hopefully, I didn't add too much filler. And I might. I think what I'll do in the when I post the video, I'll add a message in the like the status bar saying that, hey, if you already are familiar at least with what cocotb kind of does, or you already have a background in digital circuit design, I feel like for the most part you can probably skip most of the material in this presentation, or at least in this video. The next presentation, I'm gonna go over an actual example. So how does cocotb insert itself into a simulator? This leads into the example where I explain like the first cocotb test. So I think for now I'm gonna end it, and then later, probably later today or maybe tomorrow, I'll add the second video where I'll continue from where I stopped. Thanks to those who took the time to listen, and goodbye.